Very good. We can go live. Excellent. And welcome everyone to the Data on Kubernetes community live stream number 150. Yes, that's a milestone. Excited about that. Very excited about our speaker that we're going to be having with us today, as well as a couple of announcements that we definitely want to let everybody know about. We've got a lot of things going on in the community, getting closer and closer to KubeCon. So that means we're very, very busy with lots of things happening. If you have not signed up for KubeCon, it's very easy to do so. Please, please, please check out the link that I've shared here in the chat. So that way you can get all the info that you need about the schedule, who's going to be speaking, the different things that are going to be happening, all the information about registration, whether you're going to be joining us online or in person in Detroit. The event will be on October 24th. It will be live streamed through a special link that you will get if you register on the CNCF website. If you're going to register in person, if you have any difficulties, any questions about that, as always, you can reach out to us on Slack. That being said, we've got a lot of things to talk about today. Our speaker today is no stranger to the Data on Kubernetes community. He will also be speaking in DoK in Detroit, and I just found out we'll be there in person. Very excited, as always. He is the CEO of anynines. His name is Julian. Welcome to live stream number 150, Julian.
Well, that's awesome. 150. That's a very great number. So thank you for having me.
Yep, it's important to have a special person for a special day. And you certainly are a special person, riding your motorcycle from Saarland to Valencia, where we last saw each other in person in May. We were talking before we got started about Julian's motorcycle diaries, his motorcycle experiences. He has a very cool motorcycle. But apart from that, for people who don't know you, can you just give us a little bit of background, who you are, how you got into the Kubernetes ecosystem, data space, whatever you want to mention?
Yeah, well, we actually a company building application development platforms for a living. So Kubernetes is an obvious choice these days. We've been, engaged in data service automation since more than a decade. We started with manual operations, transitioned to Chef and Puppet. We did a lot with OpenStack. Then we transitioned to the Cloud Foundry ecosystem. We're still doing a lot with it, especially with BOSH, declarative virtual machine automation. And for a few years now, we're investigating, expanding our product range to Kubernetes as well. So building operators and automating data services is basically daily business for us. And I'm happy to share some of the learnings along the way.
All right, good. That being said, you've been around this sort of space for a while, and we're gonna, maybe towards the end of the live stream, look at some of the things about, what's going to be coming next. What are the questions that still need to be answered? What things you expect to be happening in the coming months and years? But regarding this issue of running stateful workloads on Kubernetes, as someone who's directly interacting with customers, what are some of the doubts that they often have when it comes to this topic? And what kind of information might you share that would be useful for people to have when they're having those conversations?
Well, when it comes to data, there are several strategies on how you can deal with it. Certain fraction of customers, they go all in with their infrastructure providers. And often these providers, they also offer some kind of data service automation. Now, for those companies who do not want to tie into infrastructures directly, the biggest thing you need to avoid is tying into proprietary technologies too much. And with proprietary, I don't mean, let's say, a manufacturer giving you a certain flavor of Postgres, but I mean, data services that are vendor specific that you won't get on other infrastructures at all. So when we're building application development platforms, managing the data layer of your applications is essential. So if you want to keep your data layer vendor neutral, or at least based on open standards, on open source standards, the question is, what's the best way to automate and to run and operate data services? And this is to some degree an unsolved problem. I particularly think that BOSH, for example, as this tool for declarative virtual machine management, is a very underrated technology and has been for years. Now, Kubernetes addresses this problem of declarative management of stateful applications in a similar way. So it's natural to adopt Kubernetes because it has so much traction. But when it comes to data service automation itself, there's this kind of converging between the data service itself, which become more cloud native over time, and the automation tooling along the way. So customers are often, let's say, a bit disoriented. They don't know what exactly to do, what strategy to pursue. They don't know where the pain points are. And they often try out because they need to collect experiences, and they are expensive experience they collect along the way without any help, I can say.
Very, very good answer. With that in mind, today's topic about building a simple Postgres async streaming cluster. How did this topic come about? What led you to that? And with that being said, if you want to start with your presentation, we can get that moving.
All right. I mean, the background of this talk is basically a lecture about Kubernetes I'm giving at a local University of Applied Sciences, and material we're also using to train up new engineers. Now, the idea of automating a Postgres is here not so much to build a production-grade Postgres, but it's like a guide that shows somebody learning Kubernetes, going through setting up a Postgres StatefulSet and documenting it along the way, which is basically what I did in the Kubernetes tutorial, which we share at learn.kubernetes.anynines.com. A link will be in the slides later. And this is basically a lightweight version of it because we usually take more than 3 hours to go through the material. Okay. So yeah, I can basically start with the presentation.
Go for it.
That's already the material. Great. I'll start sharing my entire screen because there will be some live demo parts as well.
Very good. And for folks in the audience, as usual, if you have questions, please get them in the YouTube chat. If not, we can always take the conversation to Slack.
All right. So you can see my screen now?
Yes, perfectly.
All right. So as I said, the primary goal of this talk is to providing a taste for developing an operator. Now, developing an operator is not something that you can just do in one day, and you have to pick up Go, you have to learn about Kubernetes, you have to learn about the data service. And a lot of people, they start playing around with all the tools, choosing a certain data service and just get their hands dirty and start. That's why there are a lot of operator implementations out there from which not every operator implementation will be maintained a lot, and not every operator is well designed. So if this talk, the idea is to educate people, at least from experience that we've made, and give a glance into operator development and a particular part of operator development, because it's surely too much for a 1 hour's talk. So the scope here will be from having a container image for Postgres to building a Kubernetes stateful set. Now that would be rather easy, but we also want to give it a little more complexity by setting up an asynchronous streaming replication with Postgres. So the non-goal here is it's not going to be anything production grade. There are many problems we just left aside as a conscious decision. So our minimum goal is to have that replica set, the stateful set with 3 replicas, where there's Postgres, 3 Postgres nodes, where there's a primary and you can write to the primary and changes will be replicated to the secondaries. As one of the constraints, I propose to use the official Postgres container image, because containerizing, a data service from source code is, worth its own talk. And also, if you automate your data services and there's already an official container image that's, flexible enough for you, you can just tie into the release cycle of that image and maintain your own part on your end. So it's less code for you to maintain. All right, so scope is we are happy if there's a 3-replica Postgres stateful set with 1 static primary and 2 static secondaries performing asynchronous streaming replication, which means there's not going to be automatic failover. I will maybe say a few things about the next steps during the talk if you want to develop that idea any further. So I'm a big fan of having a structure, or let's say a methodology when approaching things, because, for example, we at Anynines, we operate not only 1 data service, but nearly a dozen of them. So we need to have a structure so that creating new products incorporates the experience we've already collected along the way. So my personal understanding, if you want to develop an operator, there are at least those 5 stages. And this is not referring to the operator levels of the operator SDK. That's a different idea. Here, it's more about what you as an engineer have to go through if you start from scratch and you want to automate in your data service with Kubernetes. So obviously, the first thing you have to do, which here is called phase 1, would be to learn about the data service. In other words, what would a sysop or a DBA do, this database administrator? Once you know that, we'll look at, for example, we'll look at Postgres, how to set up Postgres, how to give Postgres a password so that you have, super user to work with, and also understanding streaming replication in Postgres, asynchronous versus synchronous replication, and choosing the one replication method that suits your particular requirements. So this is phase 1. The second phase would be, well, you have Postgres, you need to have a container image, so you need to containerize it. Once you have a container image and you know what to achieve, you need to wrap it with Kubernetes resources, which is then input to building the actual operator. So you're taking the Kubernetes resources and let Go code basically apply those resources against the Kubernetes cluster. And finally, once you have an operator, you still need to manage that operator's lifecycle as well. So if you have, for example, new Postgres versions, these Postgres versions will also mean that there must be adaptations in the operator itself. So just right before the talk, for example, I updated this tutorial from Postgres version 12.2 to 14.5. And I had to modify some of the Kubernetes resources to make that happen because configuration file changed during the many versions of Postgres that happened in the meanwhile. And you have to reflect this along your code base. So these 5 phases will basically cover the most important aspects. In this talk, we are going to focus on learning a bit about Postgres so that the rest of the talk makes sense, and then wrapping Postgres into Kubernetes resources. It's not about building the operator itself, but it's about knowing this is what you could do manually using kubectl to build a service instance. And the operator then basically takes that, let's call it a tutorial or script, and make it happen automatically upon the creation of a corresponding custom resource. So what would the sysop and DBA do? Well, if you start Postgres, you need to give it a password for the Postgres user. That's something we'll come back to later. But most of starting Postgres is relatively straightforward. So one thing to talk about a bit more detailed is Postgres replication. Well, we in particular here choose asynchronous streaming replication. So let's dig into what this actually means. So first of all, asynchronous replication is the opposite of synchronous replication. I'm not I don't have a textbook definition for what it is, but I think you get close if you say a synchronous replication means that every transaction you commit to the database will be applied to at least a majority of cluster nodes of your clustered instance. And only then the transaction will be committed. So basically, once the transaction is done, you can be sure that there's a majority of nodes in the cluster who have, which have, accepted your changes successfully. Now, with asynchronous replication, there's a different approach. You basically commit your change to a primary server, and you don't care on the transaction level about replication. So a simple visual of that would be you have an application developer, for example, or an application committing a transaction to the primary server. And then there's a second step happening independently, which would be to take that change and also apply it to a secondary server, which would be the replication. Because these two, the transaction and the replication don't happen in an atomic way. We call it asynchronous. So replication is asynchronous to the transaction, to the actual change of the database state. There's by definition, this means that you also have a different point in time when replication occurs to the transaction, and there must be a delay. And this delay of the secondary to the primary is called a replication lag. And we look into that a bit further because there are several ways you can organize asynchronous replication in Postgres. And the particular one we are interested in is called streaming replication. And streaming replication is setting itself apart from file-based log shipping, which has been the default in Postgres for a while. So if you think about file-based log shipping, we're talking about so-called write-ahead logs, basically files containing what changes to the database have been made. So such a WAL file contains many WAL entries, and those entries represent the changes to the database. In file-based log shipping based replication, you basically take those WAL files, transfer it to secondary, and execute it there. So you're basically batch processing all the changes, which means that such a WAL file contains a batch of changes. You transfer it to secondary and replay them there. Obviously, that makes the replication lag the size of the WAL files, and only after such a file has been transferred, the secondaries may catch up. So opposed to this, there's the ability to stream WAL entries rather than transfer the entire files. So this would require a permanent TCP/IP connection from a secondary to the primary to read all the WAL entries in a continuous manner. And this has the upside that you'll be, catching up with the primary much faster, as you'd be receiving changes much quicker. So our conclusion here is let's go with asynchronous streaming replication. So if you want to set up streaming replication, what happens is that the secondary connects to the primary and it needs to authenticate itself, and then the primary sends the WAL entries to the secondary. Of course, there can be multiple secondaries. In our case, we are aiming at a 3 replica set, so we'll have 2 secondaries. But I mean, this concept applies to both secondaries then. So the secondaries must be authenticated towards the primary. So a replication user is required. So basically, you need to set up a database user who is purpose-bound, or at least meant to represent the secondaries accessing the primary. So there's the primary user. You need to create it. Well, in phase 2, we think about the container image, but there's already a Postgres container image, so let's try to use it. Postgres container image is here found on Docker Hub. It gives you a lot of configuration abilities. We only stick to the very basics. So, for example, we need to set up a Postgres password as an environment variable. So we need to somehow store a password in a Kubernetes cluster and make this password show up under a particular password. So with that basic information, we can also already start looking into how to build this whole thing, how to wrap it in Kubernetes resources, which would represent phase 4. So that would be the big picture. We are going to, use a container image. It's the official container image from Postgres, so we got that covered. We are creating a stateful set with 3 replicas. Now, if you want to address nodes in a replica set, you also need to create a headless service. So that's, if you're familiar with stateful sets in Kubernetes, you already know that these two usually go together. The headless server sets it apart from its, non-headless counterpart. So usually a service in Kubernetes, if not stated otherwise, is basically acting as a reverse proxy. So it has its own IP address. It accepts incoming traffic and does a round robin to entry points or endpoints that are registered using a match label. You can do that with web applications, for example, that are stateless very easily. Now, in the case of databases, the headless service has a different behavior. The headless service does not come with its own IP address, but it basically resolves to DNS addresses of the actual pods. So whenever the pod changes, the DNS entries in the Kubernetes DNS will be updated and reflect upon those changes. Hence, a headless service does not have its own IP addresses, but it's basically implemented as a dynamic DNS configuration that's kept up to date in the Kubernetes DNS. We'll have a look at what this actually means, what the implications are for stateful sets, and why this really makes sense. All right, so headless service and stateful set go together. The stateful set is, the foundation and the primary aspect of the talk. It's basically a resource meant to have stateful applications. It allows you to define persistent volume claims, which will then create persistent volumes. This is where the data of the database will be stored. Now, in order to get this whole Postgres thing up and running, we'll also create 2 secrets. So secrets in Kubernetes, as you may already know, are basically similar to config maps, key value pairs. But you can, for example, also configure a Kubernetes cluster to encrypt those secrets that they are more secure. So we are creating a Postgres secret to store the Postgres password, and we are creating a separate Postgres secret to store the replication user. You could also have it, have it in a single secret, but I chose to keep them separate because they serve different purposes and represent different sets of credentials. But as I said, it's a matter of taste. We're also going to have 2 config maps. The ones, the Postgres config map will contain the actual configuration files you need to, serve to the Postgres binary. And also another config map that will contain a small script. Finally, there will be a Kubernetes job for creating the replication user. It's not necessarily the case that this would be the ideal way how to solve creating a replication user. You could also use scripts within the stateful set, which may even be a better approach, but this also utilizes and shows how to utilize a Kubernetes job, and it's at least it's a feasible way of doing it. The replication user job also refers to a very small script that needs to be executed that will then connect to the database and create the user. In this case, it's created as a container image, and that gives us the opportunity to briefly discuss how do you bring a script, a small script, to a binary. Are you creating a container image, or are you, for example, storing the script in a config map instead? All right, so let's dig deeper. First of all, Postgres, the Postgres configuration. What you have to do is basically give a Postgres conf file where you can adapt your particular configuration that you would like to pass to Postgres, as well as a pghba.conf which configures authentication details for your Postgres. Postgres utilities is basically a small shell script that distinguishes, sets apart roles within the Kubernetes stateful set. In particular, we need to distinguish between the primary and the secondaries. So this script basically retrieves information from the pod and derives the information, whether it's the primary or one of the secondaries. This is necessary because the primary needs to invoke initdb, where, for example, the secondaries need to invoke pg-based backup to catch up with the primary on startup. So in order to create a config map based on files, you can use that direct. You can just execute that qctl command. And there you go. We'll see and do that later in the talk. So once you created that config map, basically there's a key with the name of the file. Here it is pginit.shell, and its value obviously is the script. So the Postgres secrets, well, that's actually not true. Those are the files for the config map. Here's an example of the configuration file. For example, you define the Postgres HBA file location. You set the write headlog level and some other tweaks necessary to set up replication. And this is an example of a pghba.conf. This is not production grade. We are basically saying that all nodes from the same network, may perform an authentication based on username password for the user replicator. Well, this doesn't, really make sense. It would be nicer to close, down the number of hosts are able to access the database, because in many cases the network will be cluster-wide network. So I mentioned earlier the headless service, and this is basically a good example what it does. It basically creates you with those URIs, Postgres SQL minus SFS 0.PostgreSQL minus service. So the second part of the train wreck would be the name of the service, and the first parts are DNS entries, each one for each entry endpoint registered with the headless service. So with the headless service and a stateful set having several replicas, you can either address the entire stateful set with all its replicas, receiving DNS resolution to all its nodes, all its endpoints, or by having the names of the pods in front of the service name, you can address them individually. That's a very powerful thing that will be used quite often. So as I said, you need to create a replication user. So the primary needs to have a replication user so that the secondary users can log in to retrieve the wall entries. So we know that this user must exist, and it will be authenticated user using username and password. That's why we created a secret for that purpose. There are two headless services in our design. One is to access all cluster nodes, just as I said before, and the other is a pointer to primary. So just think about it for 1 second. I mean, our goal for today is set up a primary and having 2 secondaries. So your application will be able to just take the PostgreSQL minus SFS minus 0, for example, and we make that the static primary. That would be easy. However, with the idea of having another headless service where there's one pointer to the primary node, for example, by annotating the primary with a particular label or any other means to distinguish, you can dynamically set this service's name to point to the current primary. So this is what we want to do. We would like to say lay the foundation so that we can later also switch the primary pointing to one of the current secondaries. This would be necessary if you want to do automatic failovers, which is something that's sadly out of the scope for today's talk. All right. This is one of the examples on how to do that. As you can see, this version of the service defines the selector for the particular pods to be added as endpoints. And this one, it just takes the StatefulSet Kubernetes pod name, which will be the first one in the StatefulSet. And that's very good for bootstrapping the StatefulSet. You can also see that there's a comment which says role.primary. So by modifying the service and attaching this label to pods in the StatefulSet, you could later make this more dynamic and have this pointer change over time. So that's something we can try out a bit later. Is the headless service basically has the effect that if you look up this domain, you will see all the nodes in the StatefulSet resolving with their particular IP addresses, and to the speed of the Kubernetes DNS being updated, and this these DNS entries will be kept up to date. So the StatefulSet itself is pretty straightforward. In this case, we have the actual Postgres container. We have a persistent volume claim mounting the data directory, which is basically the single most aspect of running data services in a declarative manner, is to distinguish the ephemeral compute resource, which may be a container or maybe a virtual machine, from the persistent data directory that really makes up the state of the database. So with that particular design pattern, which is used for more than a decade already in automation, you can update, for example, the environment, including the operating system, and just remount the data directory so that the database server can continue to serve requests where it left off. It decouples the lifecycle of the ephemeral virtual machine or the ephemeral pod from the lifecycle of the data directory. So you can throw away the pod, you can throw away the StatefulSet, but the persistent volumes will remain. And when you recreate a StatefulSet, it will find through the persistent volume names referred in the persistent volume claim, the persistent volumes that have been left behind. So what it means is that if you delete a StatefulSet, this will not delete its persistent volumes automatically, unless you specify it to do so, but they will be left over. This creates the risk of having orphaned persistent volumes. So you need to take care of that, but it also gives you the opportunity to just fix a totally broken StatefulSet by creating it newly from scratch, and still be able to access and reconnect this service instance to the already existing data represented in those persistent volumes. Last but not least, once we've started the replication, the StatefulSet, 3 pods will spin up, but the secondaries want to connect to the primary. So we basically need to wait until the primary has started. Then we need to create the replication user. Now we do this with the Kubernetes job here. I think it would be a better way to take a config map, for example, take the script as a shell script or as an SQL script, and then invoke it during the container startup from within the container. There are special directories that the Postgres container image will go through and execute all scripts from that folder. So that would be an alternative to do it. The container image also is pretty straightforward. In this case, it refers to that small container image called A8S PG utilities. It contains a little Ruby script that's idempotent about creating replication users. Basically, what it does is it checks if the user already exists, and if so, it does nothing. If the user doesn't exist, remove it. And you can also turn it around for deleting it. And the idea is that if you need to run that script multiple times because you're in an unknown state and you would like to get into a known state regarding the existence of the replication user, you can just rerun the script because it's idempotent. Well, and as you can also see that we are mounting the Postgres secret to obtain the Postgres password, but also the Postgres replication secret to obtain the details of the replication user. At the very bottom, you can see we run the Ruby interpreter as well as execute the actual script. Now, you could have the discussion, well, this is only a script. The script has only, let's say, 100 lines of code. Does it really make sense to create an entire container image for it? And the answer is, well, maybe. In my opinion, it's valid to have a container image because, you have this entire release management for container images, and it's a good way to ship code as a best practice. During development, for example, this can be very, very frustrating if you have to, run through, this whole cycle of creating and transferring container images. This might be cost and time, wasting time. So the fun thing is if you mount a config map as a file and you update the config map, the file contents will change within the container during the container runtime. So this is, for example, different if you map config map values to environment variables in a pod. They won't change until the pod is recreated. So destroy, terminated, and a new pod is created. So mounting config maps as files give you the opportunity to access files dynamically. And if, for example, your process rereads those files repeatedly, you can use config maps during development to iterate through changes of a script much faster than you'd be able to with the container image. Just as a side note, once this, the version has been released, you can still create that container image. One thing, like this particular script that creates the or that bootstraps the StatefulSet, it needs to distinguish, as I said, between executing initDB, which has to happen on the primary, as well as executing PG-based backup, which needs to happen on secondaries. So how would you do that? In this case, I decided to read that additional label information. Well, who's the primary? And you can do that using the download API, which gives a pod the ability, for example, to read its own labels. And this is the script. This is the init script, which basically checks whether there is this particular label, or whether in this case, it's the label being the first node in the StatefulSet, because we said it's for now a static primary assignment, and then invokes initDB accordingly. All right, demo time, which basically means I have prepared a Kubernetes cluster here. Minikube runs here on my machine. So we are here in the PG namespace. There are no resources found. There's also a visual, you can see there are no stateful sets. There are no persistent volume claims, no secrets, none that matter to us, and no config maps, no jobs. All right. So the first step is we take screen a bit bigger. The first step is to create the config maps. We are creating them from files, which basically means that within this directory, there's a PostgreSQL conf file, as I've shown in the slides, and there's also a PG HBA file, like so. So by creating that config map, there it is. This is what you get. So the name is the name of the file, and the value is the content of the text file. I think you can do this up to a megabyte. So this is really only for small size information. It's not meant to be a data store. All right, so this config map exists. So we create one for the init script. So the init script is the one that distinguishes the primary from the secondary and is run within the container during the startup of the Postgres StatefulSet. And will either execute initdb if we are on the primary, or it will execute PG-based backup if we are on a secondary. So creating that config map is also straightforward, also from file. Creating a secret. Here we are using a literal, which basically means we will provide username and password here at the command line. So in production systems, you probably choose a different way to do that. All right. Also the same for the replication user. It's just that this has a username and a password, both being literals in the form of key and value. There's one thing to be reminded though, which is if you create a secret like this, all values are base 64 encoded. So if you were to edit this config map, editing these values will either trigger an error message, or if you're unlucky to use and choose base 64 compliant characters, you will set random values, well, not random, but not the values you intend, because there's base 64 encoded. So you basically need to run them through a command line, for example, base 64 encoding, and then you could also edit those values directly. But I mean, in this case, it's already handled for us. All right, so the secret's already there, which basically means we can create the service. So the service definition is also straightforward. It basically creates us a service, and it in the service specification, it annotates cluster IP to be none, which is the definition of a headless service. So the headless service does not receive an IP address, and by saying and indicating cluster IP none, this makes it a headless service. The selector for the application is Postgres -A. All right. So the services here under the network section, it will show it exists, but obviously does not have any endpoint because there's no pod matching the label app equal to PostgreSQL -a. So this is what we'll do next, is we'll create another service which will point to the primary. So here the selector could be role primary if we were to assign them dynamically, but because we will, static is fine for us for the moment, we just choose the first pod in a stateful set. So this tagging is already done by Kubernetes, so you get it for free. You don't have to do anything. These labels will be there. We'll have a look at it in a second. I already did that. No changes made, of course. So now it's time to create the actual stateful set. As I said, we are creating a stateful set with 3 replicas. So similar to replica set or deployment, there will be 3 pods in the stateful set, but different to replica sets, for example, you don't have to create a new stateful set in order to, for example, change the container image or anything. In this regard, it is more similar to a deployment in such a way that you can update a stateful set and change values. It will then, take control and create and recreate pods accordingly. It is, however, similar to a stateful set in the sense that it has multiple replicas. One of the significant differences between replicas, between stateful sets and replica sets is that in a stateful set, there's ordinality. As you have seen earlier, if you create several pods, they will be numbered. And these numbers, they are reliable, which means that there's a correspondence between a persistent volume being numbered as 0 and its pod counterpart. So you can be sure that this particular volume will always be attached to this particular pod. This is very important for us because we assume that the first node, the pod with the number 0, will be the primary. If that wasn't the case, just like within replica sets where it's a random string attached to the pod name, you wouldn't be able to do that. Ordinality also means that pods are created in that particular sequence, 0, 1, 2, 3, and so on, and they will be destroyed in the opposite direction, so 2, 1, 0. Ordinality, very important for stateful sets. All right, so let's give it a go. And let's watch it, because this is definitely the most interesting part. So you can see that Postgres stateful set 0 has been created and is ready, but subsequent pods will fail, and they will fail because there's no replication user yet. So if we go into the details, you will see the connection to the server, PostgreSQL primary, PG local, failed because the password authentication failed. So we need to create that Postgres user. We'll do that by executing the job. The job is pretty simple. It just executes the PG utilities. In particular, it invokes a Ruby script, create replication user, which is this one. Just connects to the database, and it has 2 directions, up and down, and creates a replication user if it not exists. So that's the item potency I mentioned earlier. Okay, so let's give it a try. There's the job. It's not been completed yet. The job has triggered a pod. Has not succeeded yet. So this is completions and parallelism. Basically means that you'll have one pod being executed at one time, and the pod will only be created once and only be executed once. So as you may know, there you could have job descriptors where you do things in parallel, and then you can do them also multiple times. So repeating the same task several times. If we wanted to create a failover capability so that, for example, a primary may become a secondary, you basically have to create replication users on each of the nodes, because each of the nodes could become the primary so that the other secondaries are able to log in. So that would be a way to do that, but also you need to do that on every node, which is why if I had to do it again, would potentially do it during the pod startup within the StatefulSet and not as a separate job. All right, so this one has succeeded. These pods, they failed earlier. You can see now the StatefulSet pod with number 1 has succeeded after 5 restarts. The StatefulSet basically starts all the pods of the StatefulSet at the same time. Well, I mean, why not? You could also do that in sequence, but we don't really care. I mean, they will keep failing until there will be a replication user. And once the job is completed, the preliminaries, the prerequisites are met to for the secondaries to log into the primary. Because it's the Postgres process will fail otherwise, it basically triggers a restart of the pods. So you basically have a eventual consistency behavior here. As I said, this is not how I would do it in a real world scenario, but it's a way, it works good enough here. So this one is pending. You can see he's still doing stuff. I think it's just the UI not being quick enough and refreshing. So here we go. Our StatefulSet is up and running. We have 3 replicas. This is our primary. Those are our secondaries. All right. So now what we can do is we connect to the primary. As you can see, it's using the primary service. Here's one database. Per default, it will go to the Postgres database. There's no relation called company because the database is empty. In a second pod, I'll connect to the secondary. There's no relation secondary on relation called company on the secondary either. So let's create it. So we create a table called company and we insert a record. Record is called anynines. And if you just retrieve it and selecting it, this is what you get. And on the secondary, which is a different pod, now this entry also exists, which basically means that the replication works. So that's basically the demonstration that we have set up the replication. Now, what we can also do There's this little pod I've created. It's called inspect. It is a container image that has some network utilities. And as you know, there is a service called PostgreSQL -service. And this service has 3 endpoints, 7, 8, and 9, which corresponds to the pods created in that stateful set. So if I do ns lookup on this headless service URL, this is exactly what I get. I get DNS entries for each of them. If I were to manually delete one of those pods, simulating a pod failure, it will be recreated quickly. And as you can see, well, basically got the same IP address. Yeah, so you didn't see the DNS entries reflect other than yeah, see, now it only has 2 entries. And it takes a while for the new pod to restart. Here we go. So here is the DNS entry lagging behind. And there you go. It took a while to catch up. So you can see if you want to have a fast failover within milliseconds, this wouldn't be a strategy to follow because it took several seconds for the DNS system to catch up with the existence of a new pod. But I mean, fair enough, it did its job and it did it quite well. So where does it leave us? Leaves us with the conclusions. Well, first of all, what we've done is we've created a Postgres stateful set with asynchronous streaming replication using the official Docker image. I think the effort was reasonable for achieving such a goal. However, we don't have automatic failover, which means we actually need a cluster manager, somebody detect some component detecting that, for example, a Postgres node doesn't exist anymore. And we need failure, we need to trigger a leader election because it could be a network segmentation that isolates 2 of the nodes from the primary, which still receives, communication from the application. And because you're writing only to the primary, that wouldn't be a problem. So the best strategy in that scenario would be to just leave the primary be. But on the other hand, you couldn't be sure that this is really the case. So maybe you want to call a quorum decision. And if the other 2 nodes decide that the primary has to go, they could trigger a new leader election, reallocating that primary position to one of the other nodes in the cluster. Well, this kind of stuff is necessary if you want to use the real potential of asynchronous replication, but it's outside of today's scope. We didn't create an operator and no lifecycle management yet. So those are things to be covered in other and future talks. As I said, what we did here is extracted from our Kubernetes training. So you will be guided through the Kubernetes essentials, how to create a namespace, how to create a context, how to create a pod, a replica set, a deployment, and their basic coverage of stateful sets. This is by no means as comprehensive as the Kubernetes documentation, but as you can see from this talk, it guides you through using Kubernetes in use cases that are somehow imaginable to be somehow purposeful, And it also shows you some gotchas and some insights that you don't see by just reading the documentation alone. So it's all written down. There are also other recordings that go into greater detail. If you want to, dig deeper into that topic, there you go. That's it from my end. So thank you very much. If there are any questions, feel free to ask.
Yeah, there are a lot of things that we could get into, but one of the things is that you're very adamant about Postgres. Have you tried this? Any of these things? Have you experienced any of the things that you shared today with other databases?
I mean, if you think about replication, you have to look at the replication implementation details of every data service. Data services, basically, they all need to solve the same challenges of distributed systems. They do it on a different level. The particularities with Postgres are, for example, that Postgres replication, in this case, this streaming replication, it's not, there's no failure detection, there's no leader election, there's nothing tied and built into Postgres itself. It just gives you the ability to transfer changes from one server to the other under the naive assumption, that the primary is still alive. If you think about more recent database implementations, you can also find those where in the client, let's say in the application connecting to the database, there is knowledge that there are multiple nodes in the cluster, so that there can be a client failover, for example, so that the client can basically talk to every database client, also committing writes. So, and then in a synchronous fashion, for example, those writes are committed at least to a majority of cluster nodes, and then the cluster will catch up eventually to all the changes. So in this regard, the challenges you will face when automating data services will be vastly different from data service to data services, but in theory, there are not so many ways on how to solve them, at least where they are. But for example, detecting a failure, it creates a certain class of problems that will repeat over time. That's why, for example, we have, in the virtual machine-based automation, which is much older than our container-based automation, we'll have a framework to address repeating issues. And I think beyond the operator SDK, there's room for best practices and repeating patterns and something like a framework to address data service automation.
Got it. Very, very good. Next question. For you, what are the things that you would like to challenge our community, the things that you would like to see resolved, the questions that you would like to have answered? What would they be?
I believe understanding a distributed system in problematic environments, especially problems created by the underlying infrastructure, is the root cause of a vast majority of issues when dealing with real world applications running data on Kubernetes. So I think the testing of poor network circumstances, of fluctuating bandwidth, fluctuating latencies, failing connections on various levels, this is the kind of stuff that needs to be understood in greater detail, and is something that I think the community should engage with.
Very, very good. Excellent. Well, as you said, this was the abbreviated version of a longer talk that you'll be giving, and there's plenty of technical details to be thinking about here today. That being said, Julian, always a pleasure to have you with us. Before we finish, though, as is tradition, we have our amazing artist, Angel, who's in the background, patiently learning alongside with us. And he created this wonderful artistic depiction of the things you talked about today, paying tribute to your amazing motorcycle. It doesn't do the full justice to the Ewan McGregor BMW monster that you brought to Valencia, but I think it's still good regardless.
Awesome. That's very nice. Thank you.
That's good. Good. So like I said, folks, you've got the link to register for KubeCon, to check out the full schedule. Julian's going to be giving a talk in person with us in Detroit. Looking forward to seeing you in just over a month. It's coming up soon. So looking forward to it. And we will be always interacting on Slack.